So we're now at the point that we want to transfer our preoperative plan as we have it depicted here on the left with reference Kirschner wires and a seating chisel path. So we have a reference perpendicular to long axis, a reference at this point which will be essentially the transverse plane for the first osteotomy, one of a variety of references which we can use for our 25-degree closing wedge. In this case, I've drawn it in where I actually want the closing wedge to be. In this situation, you could theoretically use this as a cutting guide if you were going to cut it in place. Because of the derotational component here, we're not going to do it that way today. Then we have our reference for the seating chisel, which is placed at 20 degrees off a perpendicular to the long axis, which is a critical, and that's based on a reference wire here. The reference wire is very important, obviously, for you to get the correction you want in the frontal plane, because the blade is actually doing the correction for you if you put it in the correct orientation. Our first reference Kirschner wire is perpendicular to the long axis, and that's what these triangles are for. There are a variety of triangles in the normal set. This is a 50, 40, 90. Okay. Now, at this point, I'm going to transfer that reference proximally, and I'm going to place it at the level of the initial transverse cut for two reasons. I'm going to use it ultimately for the cut, and secondly, I want it closer to my reference for the 20-degree deviation that we need for placement of the guide reference wire for the seating chisel. So I think it's really important in these models that you try to, in the proximal segment, get some of this perimeter plastic, because there's virtually no bone in the neck. And if you're using it as a reference, you'll be able to push it anywhere you want. This is clearly not the case, and even osteoporotic bone has much better purchase. And now what we're gonna do, and we're gonna bisect a 40-degree angle for our reference. So this, you have to take my word for it, that does say 40. And so our reference is then gonna be parallel to this superior surface. And I've pre-drilled this. I think we're close. Now, you can always talk about margins of error, and clearly if you're gonna carry out a frontal plane correction from varus, if you're gonna err, you'd like to go toward more correction than less. And so, and this is always the situation that you're planning for. So I would overcorrect by 2 to 3 degrees if I was worried about the position of the seating chisel. So just as a final check on our pre-op plan and our reference Kirschner wires, we have 2 perpendicular axis Kirschner wires and a guide wire, which is designed to essentially guide our seating chisel placement, which is placed proximal enough that we can go off our measuring guide and drop down 15 millimeters from the tip of the trochanter for the top of the blade plate. And we have our corrections here. Currently, we're only working on the frontal plane correction. And we're gonna go next to how, as we put in the seating chisel, how we're gonna compensate for the sagittal plane. And the horizontal plane will come as a compensation with the closing wedge, which will be done after the transverse component is completed. And then we'll carry out our 20-degree medial rotation of the distal segment before we cut the closing wedge. In a normal situation with a cannulated seating chisel, you would never use the sequence which I'm going to show you with these drill bits, because you want as much cortex as possible intact around the flutes of this blade. The beauty of the blade plate is it removes no bone and it impacts bone as the blade is inserted. So this is the original instrumentation that way it was designed to be made. You would take this triple drill guide and you would use these 4.5 millimeter drills, and then you're gonna have 3 holes sequentially, and you're gonna follow that today with a router which will then enlarge these holes so that you can easily insert the seating chisel, which is a replica of the cross-sectional profile of the blade itself. Okay, so this is our initial portion. We've drilled 3 holes. So this is our 15-degree compensation for the sagittal plane. Okay, step 2 then has been use of this router. With the power, you can sort of machine it back and forth. And the goal is to give you a little bit of freedom as you insert the seating chisel in this plane, like that. Now what you can do is you can essentially change the position in the sagittal plane by twisting with the tuning fork, this clever little device. And you can change this as much as you want in this position or in this position. And this is where our sagittal plane correction comes from, again, using the guide. This is our reference. So if we look at our correction, we're approximately parallel to the proximal segment with our 15-degree correction, and then we would have, in this position, a restored sagittal plane axis. Typically, if we're going to use a 60-millimeter blade today, you'd over-insert the seating chisels by about 1 centimeter, so you have plenty of room, and you'd go in and out multiple times, so you have a very well-worn path for the blade. If we look at where this is on this plane here, and here is the last thing you'd always do before you go anywhere else is you loosen the seating chisel. In young hard bone, if you do this after you've done your osteotomy, you get to close the wound around the seating chisel because it won't come out. Now at this point, the seating chisel is fully inserted. And what I've done is place a 3.2 millimeter drill bit distally, which subtends a 20-degree rotational correction for the anteversion. So I'm using the seating chisel or ultimately the blade plate handle itself as one portion of the correction determination, and this relatively stiff drill bit distally as the other portion. So we're going to actually, with the transverse osteotomy, we're going to cut, we're going to derotate so that these are going to then at some point be parallel, although you have to have very good control over the proximal component. And at that point, you can do your closing wedge from the distal segment. All right, so we're going to cut the transverse component of the primary osteotomy here. I think it's just fine to cut on the K-wire. It takes away a little bit of your measurement error possibilities. There are different ways to do this. You can, if you are only going to do a single plane of correction, it's much better to come down with your other reference and complete this partially to here and then come across here. Now the problem with this is that we're going to use our transverse osteotomy to compensate for rotation. So we're going to do the transverse, complete it, derotate, and then take the closing wedge. Okay, so now we've completed this component, and now what we'll do is go back to our horizontal plane. We'll take out this reference. Before we take our closing wedge, we're going to, with this position, we're going to line these up. And if you look what that does to the position of the lesser troch, because of the medial rotation, you can see where the horizontal plane correction comes in. That's too much. I can't really hold this while we're going to cut it, but you're going to have, what you can do is mount the distal segment or the proximal segment in the vise and hold the distal segment while you do your closing wedge here. So now we've completely compensated for the torsional problem. We'll end up with 15 degrees of anteversion. We now have a reference for the closing wedge, which is done after the derotation, and we're going to bisect the 50-degree angle. And hopefully these wires are going to be parallel, so this will be our 25-degree closing wedge. Okay. You can move this reference up if it's easier to here, and I suggest you do that the first few times you actually measure these corrections. And I've also placed this so that I can use it. I want a smaller closing wedge. Our plan showed that we were only going to go approximately halfway across the transverse osteotomy for the correction. So now we've done the transverse osteotomy and we've done the horizontal plane correction compensated closing wedge. And so hopefully now as we superimpose these, we'll have normal torsion, and the only thing we'll have left will be our sagittal plane correction, which will come from a secondary osteotomy from the proximal segment. So this is now our horizontal plane. So we're parallel. So theoretically, once we're done with this construct and we're plated, the total torsional profile of the proximal femur is going to be normalized to about 15 degrees. So now we're down to the final component to get our last plane of correction. So we want to get the sagittal plane, which means we have to take a portion of the anterior, we have to take an anterior closing wedge from the proximal segment to compensate, and that'll essentially, this cut will be parallel to the seating chisel, which makes it relatively easy, but it's not going to go all the way across, because remember, our point of contact is only going to be here. So we can do this almost freehand by coming in parallel to the blade, and I'm looking at the posterior cortex, and I don't want to go very far across. Okay, that's what we have now. And theoretically, when we match these up with the blade in place, we should have now compensated for all three planes. So that last closing wedge is from the anterior cortex, the proximal segment, which corrects the sagittal plane. We've compensated the horizontal plane with this cut, derotated. And our length determination has been based on offset and the angle of the correction, as well as how far across we went here. At this point, we've now attached our blade to the proximal segment and to the distal segment with a single bicortical screw with this gap. Now that gap is the method by which we can essentially translate the shaft laterally and in the process compress along this oblique fracture plane. It is possible to have done this without an anterior closing wedge. If you wanted to essentially have a single point of contact anteriorly, you could have had an opening posterior wedge and still generated mismatched compression. So you really only need one plane of compression along here, although obviously the bigger the contact area at the point of compression, the better off you're going to be. So normally you can do this as one screw. The farther off you are, the more likely it is to be safer to use two screws like you would use the sequence for tightening the lug nuts on a wheel, going back and forth between two different screws. So I'm going to put one in here and we'll see. So what will happen as we tighten this progressively, we'll translate and generate compression along this oblique plane. We're about to reach the yield point of this plastic bone. We're fully seated now, and what was previously torsionally unstable is rock solid now. Now, you saw that we had two pieces of bone generated by the closing wedge, and it is possible, if you're going to generate a large opening wedge over here, to insert this at the beginning of the case and leave it like that. Or if you have bone left over at the end, particularly if you've done much of a shaft translation, then you can actually fill in underneath the blade with the remainder of this closing wedge and cut it to size. So at this point, we have now a frontal plane correction. I've left the insertion handle on because this was our reference with our distal drill bit for the horizontal plane, which we've already checked. So if we check our horizontal plane here, we can see that at the end, we have a seating chisel handle, which became a blade plate handle. And now those are parallel, and we now have a restored femoral anaversion of about 15 degrees.